Hello everyone. In this video I am going to explain detail about the VI characteristics of the PN junction, basically the practical experiment on how we can evaluate the voltage and voltage versus current characteristics, VI characteristics of a normal rectifying PN junction diode, and that experiment we will be doing in multisim. I will show you how it can be done in multisim. Okay, so let's start. So this is your multisim platform in which we will draw the circuits. Okay, so first let us take all the components that required. So we need a diode, so just click on this diode or the library where you can see the different diodes. So diodes I want is rectifying diode. Generally we use this 1 and 4007. So let us take this. Yes, this is 1 ampere, the maximum current 1 ampere, 1000 volt standard rectifier diode. So let us take this. Okay, so then we need a resistor. Okay, so from here you just select where it is basic, and under this basic you will get the resistor. So let me take one current limiting resistor of say 1k. Along with the diode will connect, and then we need a power source. So for that power source we will call this power. Then here switches, this sources, under this sources power source. So here we need a DC power. Okay, so generic DC power. Then also we need a ground. Okay. Now there are two procedure I will show you. Let me show you the first procedure. So in this I am just connecting this 1k resistance, and so let me rotate this. Okay, so this diode, then this is being connected with this. Okay, then just connect this ground over here. So that's all. Now a multisim provides the analysis. Okay, so for that analysis you just go to the simulation, analysis and simulations. So here what we need is DC sweep. Okay, so DC sweep, in this DC sweep. So here the source voltage for the diode is V1, so it is V1, labeled as V1, so it is showing source as a V1. Then let me, because diode, as you know, this PN junction diode, particularly this rectifying diode, now I am looking at the forward bias, since this positive side of the battery is being connected with the P type and negative side of the battery is being connected with the N side. So it is so it is forward bias, and in forward bias, if it is silicon diode, this is a silicon diode. So for silicon diode, in and around 0.67 volt till 0.67 volt, the barrier does not break down. At 0.67 or 0.7 volt, the barrier breaks down. So after that, a current flows rapidly. Okay, so let me start with this variation of this voltage starting from 0, and since it is the maximum, I am giving as 12, so it goes up till 12. Then say later increment of 0.1. Okay, that is sufficient. So let me save it. Okay, so now once I run it, so it will analyze itself starting from 0, 0.1, 0.2, 0.3, like that. It will go up till 12, and current passing through this will be analyzed. Oh, just yes. So output I have to, yes, output I have not yet added. This is analysis only, output I have to add. So it is the ID current, diode D1. So my diode is D1, so current passing through the diode or the current passing through the R1, the same will be same. So edit, so it is selected, edit. Okay, so this is your output parameter, then save. Okay, now let's run it. So as you see, this is the forward VI characteristics. So almost 0 in like a 0.8. So you can add here the cursor. Okay, set cursor, show the cursor value. So you can yes, it is Okay, so in a so since it is 2, so somewhere it is 1, so at this point it is around 0.7 volts, so it gets breakdown. Till this it is 0, almost 0. Okay, and further after this it is linearly increasing. Okay, so current increasing as voltage is increasing. It's just like a ohmic contact. So this is your forward bias VI characteristics of PN junction. In this y-axis it is current, in the y-axis it is the applied voltage. Okay, now the same I'll just show you with a reverse bias condition. Okay, so in the reverse bias, just I'll alter the battery. Let me rotate it. Okay, so now negative side is connected with the positive part and positive side is connected to the negative part. Okay, so now since as you know in the negative voltage this diode does not break down at negative 12 volts, so it will be high volt. So let me put it at around 100 volt. Okay, and then go to your simulation analysis. So here start values since it is negative, let me go up till 100. Okay, so output again same ID current only. Save. Let me run it. Oh, sorry. You see here just a minute. One thing I have to make it some this here I have to make it 100 and this will be say 0. Then it will be okay, it should be less than start value, stop value, or make it no, yes, it is 0. Okay, so then yes, this side negative. It is showing the reverse direction. Let me just clear it. Okay, so we'll we have connected this battery source in the reverse bias. So negative is being connected with this and p type, the positive is being connected with the p type, n type. Okay, so now go to this simulation analysis, this is sweep. So in that source again the V1 start voltage is 0, stop voltage is 100, so let it be increment of 1. Okay, but it is in, in negative. So now if we run it, so you see this way, that means no breakdown. Okay, no breakdown. And if we this plot actually it is showing in the negative current and the positive voltage is showing actually the positive here in the curve, but it will be in the reverse. Just to flip it in like a 180 degree, then look at this, something like that. Okay, so if we go to this is your export to the Excel. So that Excel sheet will be generated. Okay, Excel sheet will be generated. You see this is the Excel sheet generated for different values of you see the current is minus 7.12. As you know, in the reverse direction the voltage is negative, current is also negative. Okay, so it is not breakdown at all. Okay, further we can increase, further we can okay, we will not save it. Further we can increase this voltage, so let it be 1000 volt, okay, and then so let it be 1000 volt, and let's see. So somewhere around 1000 it gets breakdown, Zener breakdown. So let us check in the Excel sheet the data. Let us check the data generated. So these are the data. You see, from 1050, so this same value only slightly increasing, 7 point, earlier it was 7.1 nanoampere to 7.2 nanoampere, 7.3 nanoampere, at 330 7.4, 500 7.6, 7 point, at around you see 923 7.9, then at around here 100 999 it is minus 8 ampere, 8 nanoampere, but at 1000 you see 5.8 or 0.58 microampere, this value, okay. So that means somehow breaks down, okay. So the same you can get the this Excel sheet. Let me show you the Excel sheet for the forward bias as well. Just rotate it, and in forward bias it should not be 1000 volt, it maximum can be 12 volt, okay, sufficient. Then I'll go to the simulation analysis. So 0 12, so here I'll make point say 1 0.1, and then output is okay ideally. Then I'll simulate. So it is forward your VI characteristics. So let me explore it in an Excel sheet, okay. So here in this you see, so this is 0 0.1 0.2 0.3 0.5, it is, you see, this is very low current, 5.2 into 10 to the power minus 34, then at 0.1 it is 5.2 into 10 to the power minus 8, that is that is 52 nanoampere. Then at 0.2 it is 0.49 microampere, 0.3 it is 3.9 microampere, at 0.4 it is 22 microampere, at 0.5 it is 69 microampere, at 0.6 you see it is 1 2 3 4 5 6, so 0.13 milliampere, 1.3 milliampere. Then 0.7 it gets breakdown, you see 2.1 milliampere, then it is increasing, linearly increasing, 0.8 3 milliampere, 3.8, your 4.7 5.7 6.6 7.5 8.5 9.4 1 milliampere, sorry 10 milliampere, 11 milliampere, 12 milliampere, 13 14 15 16 17 18 19 20 21 22, like that in milliampere it is increasing up till this 0.01 ampere, okay, till 12. কি মাজতে মাতি আছা কিয়? সেইফালে যোৱা, মই কিবা এটা কৰি আছোঁ, নাহিবা ইয়ালৈ। So that means forward characteristics is done. Now I'll just show you how we can do this same in our laboratory experiment, okay. So this is in the multisim, that facility is there, directly you can do it, but in lab what we'll do? So what we'll do is I will use this power supply fixed volt, or you can have the variable power supply. Say for the time being, suppose I am having only 12 volt fixed power supply. So therefore, to make it variable, what I will do, I will use one potentiometer. Okay. Okay, so I will use one potentiometer, that is your variable resistor. So let me take a 1K pot. Okay, so this 1K pot, I will just flip it. No, this is not. Okay, just a minute. Register variable register. Potentiometer, yes. So let me take this 1K potentiometer. Okay, just rotate it. So this is connected with this, then this is with this. Okay. Then this will be connected with this. Okay, now what I will do is I will use one voltmeter and an ammeter, so to measure the current and voltages. Okay, so what I will do is how much voltage that you are applying. So I'll just connect indicator, voltmeter. Okay, so this digital voltmeter you can connect. This digital okay, this I will not use. This one only I will use. Voltmeter, then ammeter. So this ammeter will use. Okay, so ammeter I will use here. So this is your ammeter. Ammeter I will be using here. Okay, so current will, so this will measure the diode current I2, sorry, ID, diode current ID. Okay, and this will measure the voltage across the diode. So I can connect this with the here, voltage across the diode. Okay, so you have to connect one ohm current. So this is the voltage across this. The thing is that this voltage from 0 to 0.7 it will vary, because this voltmeter will show the voltage drop across the diode. Now once the diode is breakdown, at say 0.7 volts, so this voltage is no longer increase, even though you are increasing the voltage here. So what will happen here, this is a 12 volt fixed power supply. So this 12 volt fixed power supply is connected through a resistor here, and variable resistor potentiometer. So the voltage at this point with respect to this will be changing according to the variation in this potentiometer. So there is a slider by which you can change it. So if it is in 0, that means here it is applying 0 volt. So 1%, 10%, like that. So I'll just this is 1K key A. So here I'll make it say 1%. So 1%, 1% it will change. Say 1% of 1K, like that. 1%, 2% of 1K, like that. The resistance will change, and accordingly the voltage drop, because it is a fixed supply. So voltage drop across it will be changed here, and that voltage is applied to the diode. So from 0 we will see, okay, from 0 we will see, and so therefore to see the voltage here we need to connect one more voltmeter here. Okay, so this voltmeter I will be connecting here. So this voltmeter U3, this voltmeter is for measuring the applied voltage to the diode, and this voltmeter is the voltage across the diode, and this emitter is the current passing through the diode. Okay, so now let me these things they are 0. So let me save it. Okay, let me do one thing. I'll open a Excel sheet where I'll put the values. Okay, that is how we do in the lab, actually in practice, physical lab. Okay, so this way we connect. Actually in multimeter we connect here in the lab. Here actually I am connecting emitter voltmeter. Okay, so what I will do here is cell number. Okay, then applied voltage, let me put it as Vs, source voltage. So here I will put Vd, voltage across the diode, and here current through the diode. Okay, so let us take few readings. Okay, some readings will take. Okay, anyway. Okay. Okay. So this is your circuit, right? Okay. Just a minute. Okay, just a minute. Okay, so let's start the simulation. So let me run it, since it was there like that. That is why that cancel. Okay, let me deactivate this. This is it. Just a minute, I'm not sure how to. Okay, let me cancel this. Okay, so let's run it. I have removed that active analysis bar. Now I'll record in the Excel sheet. Okay, so let me run it. So now it is in 0%. So since it is in 0%, no, something is wrong. How this 12 volt? Okay, this potentiometer is connected in opposite direction. Okay, let me just correct it. This should be in the opposite. I mean, just a minute. Okay, now it will be okay. This is the slider for the potentiometer. Okay, so now see, so it is in 0%. So voltage applied to the diode is 0, almost 0, 1.2 microvolt. Then current passing through the diode is 0.212 picoampere. So it is almost 0. Voltage across the diode is 1.2 microvolt. Now I am just slowly increasing it. So let me put it in 1%. Let me do it as 0.1%, then it will be good. Okay, so now I'm just okay, so let it be 0.216 volt. Okay, so 0.216 volt. So first reading is 0.216 volt. So suppose this is Vs is in volt. Now Vd is your 0.215 volt, 215 volt. Id is your 0.694, 0.694 microampere. Okay, then I am just slowly increasing it. Say okay, let me put it as if we can make it a little broader, it will be good. This slider let's see this Okay, now so it is at 0.0%, 0.216. okay, I have recorded. Then 0.413, okay, so 0.413 volt. Then your VD is 0.397, 0.397. Your ID current is 0.034 milliampere. Okay, now let's check again. So now it is 0.431, so 0.431. then your diode voltage is 0.397, then your ID current is 0.034 milliampere. Okay, let me show you. Just once you increase, you see slowly you are increasing. It is 1 point, okay, let me put it as 0.639. you see at 0.639 it is almost the breakdown. Current is slowly increasing. Voltage across the diode is 0.471. so let me increase little more. .83, so then also it is 0.503. you see it should not go beyond 0.7. okay, current will be increasing. you see now, see this is still 0.537. This is now 1.2 volt here. Current is increasing. Okay, so likewise it is increasing. Well, without using this potentiometer, I'll just show you a better way. Okay, that would be better to make this Excel, I mean the data. Okay, so this sliding is little difficult here. So what I'll do is I'm just removing this potentiometer. Removing this potentiometer. This voltmeter also then not required. So what I'll do, I'll connect this with this directly. Okay, this is your this 1K is just current limiting resistor. Okay, now what we'll do, I'll directly changing here. So I'll start with 0. Okay, so 0 volt, 0 ampere, and 0 volt across the diode. Okay, now I'll just, so here what we got is at 0. Okay, so 0, this is also 0, this is also 0. Now I'll make it as 0.1, 0.1. okay, 0.1. so 0.1 it is 0.056 micro volt, and 0.056 microampere and 0.01 volt. So what I am giving here, 0.1 volt. so 0.1 volt means here 0.1 here also 0.1. I mean VD is also 0.1. current is 0.56 microampere. okay, then I'll make it as 0.2. okay, 0.2. so if I make it 0.2, then 0.2 volts. So VD is showing how much? VD is 0.199, 0.199, and current is 0.5 microampere, slightly less than. Okay, now I'll make it 0.3. Okay, 0.3. Now see, so 0.3 is 0.3 is your earlier in the 0. Okay, that reading I can consider here. Okay, 0.216. Here VD is 0.215 volt, current is 0.694 ampere microampere. Now at point 3 it is 0.296 volt, 0.296 volt, and current is 3.94 microampere. Okay, so now I'll make it 0.4. 0.4. Then in 0.4, 0.4 volt. So 0.4 volt, your current is 0.023 milliampere. You see, current start increasing, 023. Now it's a milliampere, and your diode across voltage is 0.377. It is also increasing, 0.377 volt. Okay, now I'll make it 0.5. So 0.5 volt. So before that I can use this too, because it is already there, the reading 0.413, 0.39, it is increasing, you see. Okay, so now 0.5, current is 0.07 milliampere, 0.7 milliampere. This current also here also it is 0. Okay, and the voltage is 0.43, 0.43. Now again I am increasing, so it is I am making it to 6, so it will be almost breakdown now. So you see it is 0.06, 0.6, it is 0.462, and here it is 0.138, 0.138 milliampere. Then you make it 0.7. So this is not exactly theoretically the breakdown voltage. Okay, so you have 0.7, 0.7, it is 0.217, 0.217 milliampere is the current, and 0.483 is the voltage across the diode. So now onwards, if I make it increasing, almost the voltage across the diode will be fixed, you see. So now 0.8 I have given, so 0.8, the current is 0.301 milliampere, voltage across the 0.499. I'll make it now 0.9. Okay, so then at 0.9, it is 0.389 milliampere, 0.389 milliampere, and the voltage is 0.51, 0.511. Okay, then I'll make it 1. So 1 volt, then in 1 volt So it is, current is here increasing 0.479, and voltage across this will be almost fixed. You see 0.521, 0.521. It will not increase now. So now I'll make it 2, then. So for 2 volt, it is current is increasing 1.428 milliampere, and voltage across this is again, you see, almost same, 0.572, 0.572. Then again further I increase it to say 3 volt. Okay, 3 volt, it will be 0.596, slightly increasing, 0.596, and it is 2.4 milliampere. So current is sharply increasing, linearly increasing. So now make it 4, so for 4 it is 0.612, and it is 3.388 milliampere. Okay, so let me take up till 12. Okay, so now I'll make it 5, then in 5 it is, diode voltage is 0.624, slightly more, then 4.376 milliampere, then I'll make it 6, so for 6 it is 0.634, and current is 5.366. Then further I'll make it 7, so then at 7 it is 0.642 that voltage, and 6.358. Then further I'll make it 8. Okay, so in 8 it is 0.648, and 7.352 milliampere. Then further 9, so at 9 it is 0.654, and 8.346. Okay, then 19. Okay, at 10 it is 0.66. So you see from here it is almost fixed. From here after the breakdown it is slowly increasing, but before that it is increasing. Okay, now it is current is increasing now, 9.34, and then make it 11. So at 11 it is 0.664, and it is 0.01 ampere. Okay, then at 12 it is 0.669, and it is 0.011 ampere. Okay, so as you look at this, okay, so now I'll plot it. Okay, so I'll plot it in the Excel. Let me change this. Okay, anyway, if you plot it, obviously you have to make it like, no, these are involved, all are involved, these are also involved, but these are microampere, so it has to be 10 to the power minus 6, so E minus 0 6, okay, minus 0 6, so here also minus 0 6, here also E minus 0 6, and then here also E minus 0 6. Now here it is milliampere, so E minus 0 3. Here also it is E minus 0 3, that means 10 to the power minus 3. And then here also E minus 0 3, E minus 0 3, E minus 0 3, now this is your ampere, so it will be like this only, it will be like this only. Okay, so here what we'll plot is, we'll plot this and ID. Okay, so insert plot, you see, it makes it just opposite. just a minute, I'm not sure how. Okay, so now in I have this my x data here from this Excel sheet. This is my x data vs and this is my y data. So this is y data. Now I'll make this plot. I'm making it in MATLAB. So just I'm plotting x and y. Somewhere here it is breakdown, as you see. It is 0 and somewhere here it is 0.67 and it is breakdown. Okay, so I can just show you some grid. Few more options are there, we can make it later on. Okay, somewhere it is 1 here, so somewhere here it is 0.67. Then what you have to do, you have to draw a tangent here and then find out the gradient. So reciprocal of the gradient, because it is del id this side, del v as this side, so v by I it will be rd. So reciprocal of the gradient here will be the diode dynamic resistance. So what you need to do, you need to take a transient, then like this. So this way vertically it will be del id and this way it will be del vs. So del id by del vs, reciprocal of that del vs by del id will be your diode dynamic resistance. Okay, so that's all now. Thank you very much. If you find any difficulties, then let me know.